Okay, so here's what we were talking about last time. Talking about orthonormal bases, and we made a definition. Remember, we have this idea of orthogonality. Orthogonality just means dot product equals 0 in Rn. So in an inner product space, inner products playing the role kind of like dot products, inner product equals 0. Natural choice for this idea of orthogonality. So an orthogonal basis is exactly what you think it is. It's a basis where the vectors in it are all pairwise orthogonal. So the sort new idea is this idea of an orthonormal basis. And this is semantically very natural, really. Orthogonal, right? But where furthermore we want all the vectors to be normalized. Normalized meaning that we've divided by their norms to make their resulting norms equal to 1. Okay. All right, so we saw some examples last time, and more importantly, we saw this theorem. And this theorem is surprisingly important. That says that when you have an orthonormal basis, and this only works when you have an orthonormal basis, but you can find coordinates with respect to that basis by way of simply finding projections with respect to that basis. So why is this useful? Well, the algebra of these kinds of calculations are completely different, right? The algebra for how you find coordinates. You write down this linear combination. I want to view this as a linear combination of these, and how do you get your foot in the door on doing that calculation, right? How do you figure out what those coefficients are? That's a certain kind of a challenge. On the other hand, finding the projections, it's a different kind of a calculation. In a lot of situations, much more straightforward and natural. Okay. Namely, specifically, you're just computing inner products. Okay. So, then I mentioned a couple of situations where this is used. Turns out, Fourier Series that some of you all saw back in Calc 2. If you took Calc 2 here at Duke, then you should have seen Fourier Series. If you took Calc 2 elsewhere and did not take it at Duke, you probably haven't seen Fourier Series. But the idea is that periodic functions, we speculate, can be written in some sense as a linear combination of sines and cosines. And if so, how would we go about actually realizing that? How do you find what the coefficients are by which some function is a linear combination of sines and cosines? Well, you're looking for coordinates. And it turns out that sines and cosines, as used in Fourier Series, make an orthonormal basis if you adjust accordingly. And so you can do Fourier Series by computing some L2 inner products. Anyway, so if you haven't seen Fourier Series before, you will see them in Math 353. Most of y'all will take Math 353. If you have seen them before, that's where those formulas came from. The other example, and I think this is really good to know, one of the big ideas in image compression ultimately comes from this, that there are clever ways to view images as being a vector space. Vectors in a vector space. Kind of weird, right? But we've seen plenty of weird vector spaces before, right? So if you view images as being vectors in a vector space, the vector space of all images, and there's an appropriate and very reasonable way to add images. It's just superimpose and sort of add. One good way to do image compression is to find how to write the image that you're interested in as a linear combination of simpler images, right? And specifically, simpler images that form an orthonormal basis of image vectors. So lots of details ensues on that. But anyway, that is a very powerful way, a very surprisingly effective way to do image compression, is ultimately, again, with this theorem. Okay, all right, moving along. So here's another connection, another neat fact about orthonormal bases. I'm going to make a definition. By the way, the definition I'm going to make here is a little bit different than how the book does it. I'll comment on that in a moment. But suppose you have an orthonormal basis. If you take the vectors of that orthonormal basis for Rn and just make a matrix out of them. like this. The resulting matrix is what we call an orthogonal matrix. Now, before I go on, I will make a quick complaint. Doesn't it seem like this matrix, whose columns form an orthonormal basis, doesn't it seem like this should be called an orthonormal matrix? Right? I feel like it should. I feel like this should be called an orthonormal matrix. Awkwardly, it's not. Awkwardly, this is simply referred to as an orthogonal matrix. And I asked a question one time, colleagues. I wonder why no one ever gets confused and thinks that, maybe if you say orthogonal matrix, it's referring to a matrix whose columns are merely orthogonal and not normalized. And the response I got was, what a useless concept. Why would anyone ever think of such a thing? Right? So anyway, it's an awkwardness of terminology. Please be aware that even though the columns are an orthonormal basis, people will only say orthogonal matrix, and you have to just remember that it's orthogonal and the columns are furthermore orthonormal. Okay. All right. Neat fact about orthogonal matrices. If you have an orthogonal matrix, that matrix has as its inverse its transpose. Super weird. Now, before I go on to proving this fact, I want to talk about how shocking this is. In the past, now we know how to find inverse matrices, right? We have a process. This goes all the way back to chapter 1. The way you find an inverse of a matrix is you take your matrix, you put it here, then you put the identity matrix next to it, and then you row reduce the whole thing. And if you get down to the identity as the reducer echelon form, then whatever is over here on the right as a result of that those row operations, whatever's on the right, that is your inverse matrix. So we have this whole sort of row reduction process that we justify from the point of view of interpreting row operations as elementary matrices, and there's a whole sort of thing there, right? What this theorem is saying is, yeah, but if the matrix is orthogonal, you don't have to do that. All you have to do is just transpose the matrix. That's it. This is how you inverse an orthogonal matrix. Just transpose it. Rows become columns, columns become rows. This is so surprising as to seem implausible. Right? How could it be this easy? It seems like we should have to go through a whole song and dance like we did in chapter 1. So here's the argument as to why this is true. It's ultimately a very straightforward argument. Let's just write down A transpose A. Right? Now keep in mind A is orthogonal, so A has a bunch of column vectors that make an orthonormal basis. Right? Now what is A transpose? Well, A transpose is going to look just like that except transpose, so those same what had been column vectors are now row vectors, same orthonormal basis. Right? So there's A transpose A. How do you do the multiplication? How do we multiply this out? That product. We compute that product one entry at a time. If you're off the diagonal, I want to compute the ij entry of this product, where I and j are not the same. Think about the old high school definition of matrix multiplication. That means I'm looking at the ith row of the left matrix, the jth column of the right matrix, and in this case, for example, it might be, let's say, the ith row of the left matrix corresponding to what row we're in there, the jth column of the right matrix corresponding to what column we're in the product. And notice what you've got is a dot product of two of those basis vectors. And if this is an orthogonal basis, in fact it's even more, it's an orthonormal basis, that dot product is 0. Orthonormal basis, vectors are orthogonal, dot product is 0. Okay, so these off-diagonal entries are all They're all zeros. All of the entries off the diagonal. Now, what about, let's see here, hang on. What about if you're on the diagonal? Right, what do you get here on the diagonal? Well, on the diagonal, we're looking at, again, row dot column. But just now, being on the diagonal, whatever row we're in, we're also in the same column number. So whichever row vector we pick out there, we pick out the corresponding column vector over here. So that turns into not vi dot vj, but vi dot vi. Same vector dot itself. So we get magnitude squared of that vector. And keep in mind, this is an orthonormal basis. Magnitudes are all 1. And so we get 1. So, nice result. We get all 1s on the diagonal. We get all 0s off the diagonal. Both of these results, right? We know why do we get 0 off the diagonal? Why do we get 1 on the diagonal? Because the basis in question is orthonormal. In both cases, it's what's sort of the orthogonality that gives you the 0s, and it's the normality that gives you the 1s. Punchline, though, we get the identity matrix. Right? So, altogether, A transpose A is the identity, and therefore A transpose is A inverse, as required. Oh, that's lovely little proof. Anybody have any questions about that so far? All right. Now, another little quick observation before I go along. So we have here a definition. This is my definition of an orthogonal matrix. And then here we have this theorem about orthogonal matrices that A transpose A is the identity. Okay, so I just want to point out the book switches these. And it's not a matter of right or wrong. This is just a matter of choice. These are equivalent statements. So a matrix having the feature that its columns form an orthonormal basis, a matrix having the feature that its transpose is its inverse, these are always simultaneous. Any matrix that has one has the other. So I have chosen to make this the definition and this a theorem. The book chose to make this the definition and this a theorem. Ultimately, it kind of doesn't matter. I mean, they're equivalent definitions and equivalent results. Okay, the reason I do it like this is that to me it's ideal for a definition to be motivated, right? And if you look at this definition that I've got here, it's, mostly motivated. Why we would call this an orthogonal matrix? Well, because the columns are orthogonal. Right? Well, they're also normal, and there's that whole thing there. But the orthogonality word comes naturally out of the definition that we're making. When the book writes as a definition that any matrix whose transpose is its inverse, we define to be an orthogonal matrix. It's not clear why they would choose that word, right? And then they, subsequently show that the columns have to be an orthonormal basis, and then you're like, oh, okay, that's why they define it that way. But anyway, just aesthetics, I'd prefer for the definition to be the one that's most easily motivated in the language. Okay. All right. Okay. Another neat fact about orthogonal matrices. Orthogonal matrices preserve dot products. Now recall, in general, matrices don't preserve dot products. You take a couple of vectors V and W, look at their dot product. Take those couple of vectors, multiply by some matrix A, and then take the dot product. Well, of course you're going to get wildly different answers. Vast majority of the time. Right? So amazingly, though, an orthogonal matrix, you always get the same thing. And you can see in the result that we have here what I'm talking about. If you have vectors V and W, AV dot AW is equal to V dot W. Okay. Now, I'm going to prove this fact for you In order to prove this, I need an algebraic tool that we've never written down before. We've kind of never needed it, so we've never bothered. But here's the little algebraic tool that I need. If you have a couple of vectors and take their dot product, this can be viewed as the transpose of the left vector, thought of as a matrix, and then matrix multiplied by y. All right, now let me show you why this is true. It's ultimately not very deep. The dot product, right, you take the two vectors, the x and the y here, and when you write the elements and you multiply and add in the usual way. Okay. What is a matrix product here? X transpose y. Well, X transpose looks going to look like that, right? X transpose. We're going to take the vector x that was a vertical column vector, transposing it makes it a row matrix, right? And then matrix multiplying that by y, which is a column, right? How do you matrix multiply this single row matrix by this single column matrix? Well, it's the exact same arithmetic. You sort of multiply and then add the exact same arithmetic that you would go through and do here. Right? So this is ultimately not a deep fact asserting that a dot product is a transposed matrix product. It's just the observation that, well, this is multiply and add. It's the same exact arithmetic in both cases. So while it's not deep, it is handy in lots of occasions. Here's one of them. Here we have a dot product. You see here I've rewritten it as a transposed matrix product, and then the algebra just ends up working out really nice. So a transpose of a product is the product of the transposes. Right, that's an old fact from chapter 1. I can move parentheses around. Notice that I now find myself looking at A transpose A. Wait a minute, this is an orthogonal matrix, and orthogonal matrices have the feature that A transpose A is the identity. So this A transpose A disappears in this product. We're left with nothing but V transpose W, which of course is V dot W. Guys, this is a very convenient little algebraic sort of sleight of hand. Makes everything work out nicely. How we doing? Everybody on board? Okay, notice it was critical that we be able to make this go away, right? The A transpose A being the identity was essential. So this result only applies when that holds. Namely, this only applies for orthogonal matrices to get this result. Now, why do we care about this? Well, for one thing, it's algebraically kind of interesting. But the fact that it preserves dot products has some nice geometric upshots. Preserving dot products. If you have some process, you've got a bunch of vectors over here, and there's something you do to them that produces all new stuff, but in this process, if dot products never change, then furthermore, anything that you compute from dot products will also never change. Right? If the dot products are the same over here as they are over there, anything you compute from the dot products, same fact. So what do we actually compute with dot products? Well, we compute a bunch of things with dot products. Lengths, right? How do you define how do you compute anyway the length of a vector? It's the square root of the self dot product of that vector. Right? So it's computed with dot products. So orthogonal matrices preserve dot products. They also preserve lengths of vectors. That means they preserve all distances. By the way, likewise, angles. You can compute angles exclusively with dot products, right? Using that arc cosine formula. That means all lengths and all angles are also preserved. So this action of, multiply by an orthogonal matrix, this process of multiplying by an orthogonal matrix preserves all distances and all angles, and so it's what we call a rigid motion. right? So if, for example, I mean, if you were to take my hand here and think of, maybe that's the origin, and every point in my hand I think of as being a vector. If I were to multiply everything, all these vectors that are my hand, if I were to multiply by an orthogonal matrix, it would be like I'm doing something like this with my hand. I'd be a rigid motion, so I wouldn't be doing nothing weird like this, no stretching or anything like that, none of that, right? It'd just be rigid motions only. Yeah. Right. Okay. Alrighty. So that's kind of a neat fact. By the way, this discussion in here is, if y'all haven't noticed, we're quite a bit behind schedule. So this discussion is highly supplemental. It's not in the book at all. If you're curious, come talk to me, but we just don't have time to talk about it. We've got to get into kind of catch-up ball mode. So anyway, if you're curious, this is a fun argument. But okay, we're going to move on to Gram-Schmidt Orthonormalization. This is a big word with a surprisingly small meaning. If you have a basis that is not orthonormal, and by the way, sometimes it's hard to find a basis, depending on what kind of situation you're dealing with. If you're talking about Rn, sure, right, it's easy to find bases. But if you're looking at, solutions to a differential equation, let's say, and it's all you can do to get a basis, right? Well, it'd be nice if we had an orthonormal basis. If we had an orthonormal basis, we could do all this cool stuff that we just got through talking about. Among other things, we can compute components with projections, right? So that's really nice. So if I have a basis that's not orthonormal, how do I take it and manipulate it around and find from it an orthonormal basis? So that's the word orthonormalize. Right, I want to take something that's not and turn it into something it is. Orthonormal. So that's the word. Okay. So this process, Gram-Schmidt Orthonormalization, by the way, there's a related idea called Gram-Schmidt Orthogonalization. I think orthonormal is better than orthogonal. So let's not set our sights too low. Right? And conceptually, it's actually a little bit easier to orthonormalize than it is to orthogonalize. It's just slightly easier. So this is both easier and better, so I figure it's a natural choice. Okay. All right. So here's the idea. And by the way, be prepared for disappointment. When I first heard this term, Gram-Schmidt Orthonormalization, I thought, wow, that sounds sophisticated. Right? That's a lot of syllables to dedicate to a concept, right? So surely there must be something really deep and subtle going on here. And then I saw the process and I thought, really? Is that it? Really? That's the whole thing. Okay, wow. In terms of number of syllables on the name per unit depth of concept, this is about as high as it gets. All right. So here's all it is. It's not a deep concept at all. What's wrong with that vector? W1. Let's just fix these vectors one at a time. What's wrong with W1? Well, it's not a unit vector. So let's take that vector. Let's divide it by its own magnitude. Now I have a unit vector. Right? Not a deep concept. Okay. All right. Now, so this first vector is fixed. All right, next idea. What's wrong with the second vector? What's wrong with this thing? Well, there's two things that are wrong with that vector. For one thing, it's not a unit vector. For another thing, it's not orthogonal to the first. I've already fixed V1. I'm done with V1. I don't want to have to go back and change V1. So given that V1 is fixed, I need to turn this thing that's not perpendicular to it into something that is perpendicular to it. So here's all we're going to do. We're going to take our fixed vector. We're going to take the vector that we want to subsequently fix. We're going to identify how much of that vector that's not yet been fixed, how much of W2 is actually pointing in the direction of V1, and then let's throw that away. Right? We'll subtract purple minus blue, And the result, purple minus blue, this result has no component in the V1 direction because I threw away the component in the green direction, in the V1 direction. So if you identify the V1 component, toss it, what results has no V1 component and therefore is orthogonal. That's the big idea. Right? It gets very disappointing, and of course now, the result is not a unit vector, so you're going to have to fix that too. So this, what had been not a unit vector, divide it by its own magnitude, and now you have a unit vector. And now you have an orthonormal basis. So this is the big idea. Gram-Schmidt Orthonormalization is just identify what you don't like and throw it away. That's it. Yes?
Why are you allowed to do that?
Oh, why am I allowed? It's a free country, and I want to, and it's legal. So, I'm sorry. Yeah, no. Okay, are you wondering why? How do I know that the result is still a basis? Perhaps. Okay, that's what you meant. I'm sorry. Yeah. Right. Okay. Yeah, that's a great question. So that's a fantastic question. Once I write down the formula for how to actually do this, let me come back and answer that question then. Very good question. Okay. All right, so details. How do we actually execute this? Now, again, the first part of it is very straightforward. If you have a non-unit vector, W, and you want to turn it into a unit vector, V, divide that non-unit vector by its own magnitude, bam, you got a unit vector. So the first step is always an easy one, right? Just normalize that vector. Okay. All right. The next step. This is the sort of the one where we have to write something down. Okay. So we've got this vector here, and I would like to identify that vector there. Right. I would like to identify. Let's see here. The vector that points in the direction of V1. You'll notice. Right, this blue vector points in the same direction as V1, and its magnitude is, it's the component of W2 in the V1 direction. I want to know, to what extent does W2 point in the V1 direction? That's how much V1 I want to get rid of. And these are both calculations that are pretty straightforward. So let's see here. So this distance, that distance there is just, how much does W2 point in the V1 direction? That's a projection, a component, depending on which Math 212 terminology you like better, and it's computed with an inner product. Now you might be thinking, wait a minute, isn't it inner product of W2 with V1 divided by the magnitude of V1? Don't you have to divide by the magnitude of that vector? Don't forget it's a unit vector. We've already unitized it, so we'd be dividing by 1, so no, we don't have to. Right. Okay, let's see. So that's the magnitude, and the direction, of course, I'm looking for this vector to be in the same direction as V1, so that unit vector direction is V1. Real simple formula. This is the nugget. This is the big idea. All the steps that we're going to do in Gram-Schmidt Orthonormalization ultimately is this, that the thing you want to throw away. And notice, by the way, the thing that we are subtracting here, right, this vector is what I'm subtracting from my original purple vector. The magnitude is a projection. It's a component, right? And the direction is just, the already unitized vector. That's the big idea. Very disappointing in a way. But so just remember that little construction. Having subtracted, then notice this difference is that vector there. And how do I then normalize that? Well, again, that's pretty straightforward. You take a non-unit vector, you normalize by dividing by its own magnitude. All right, is everybody on board? Okay. Okay, so now let me answer your question. How do I know that this results in a basis? So what I'm going to do is let's look at this resulting. Let's see here. Let's look at this resulting basis V1 X2. Where does how do I represent that basis in terms of V1 and W2, right? So V1 and W2, we already knew V1 and W2 was a basis because that was pretty much our original basis except for a scaling, right? So what happened here? Well, if I look at all of this in coordinates with respect to the original basis, notice that I'm effectively multiplying by a matrix. The first vector remains the same, right? The second vector, I'm still keeping W2, so my second component is still going to be 1, and then I'm subtracting a certain formula. My second vector is going to be itself minus some multiple of the first vector. So I am effectively multiplying by this matrix, and that matrix has determinant 1. And that's ultimately the point, that turning the one basis into another basis comes by way of a matrix that's not singular. So definitely still a basis. Yeah. Okay. All right. Y'all don't have to worry about that. This is, you can the rest of the details of the proof that this is that orthonormalization process results in a basis is not something we know that we're going to test y'all on. Okay, so that's the process. Now you will notice that I started here with a basis consisting of 2 vectors. So we now know how to Gram-Schmidt orthonormalize a 2-dimensional basis. What if I have a 3-dimensional basis? Again, disappointing. It's the same process. Fix the first 2 vectors in exactly the same way. You fix the first vector by normalizing, just normalizing. You fix the second vector by throwing away the appropriate portion in the direction of the first vector, just like on the previous page. And then we find ourselves with this new problem. How do we fix that third vector? Well, that third vector, there's 2 things that I don't like about it. What I like about the third vector is the part that's perpendicular to the first 2. What I don't like about it is, well, there's a component in the direction of V1 that I compute by the exact same formula I used on the previous page. And there's a component in the direction of V2 that I compute by the exact same formula from the previous page, right? So now that's the big difference. If you're looking at the third basis vector, you need to fix it with respect to both of the previously fixed vectors. So you're going to have 2 components to get rid of, and the formula is exactly what you would think. You take the original vector, subtract the light blue part that you don't like, subtract the dark blue part that you don't like. The result is the one that is now fixed with respect to direction anyway. And then, of course, normalize at the end. So the final third vector there is just normalized. Okay, so that's the process. And now it's a matter of just execution. A quick observation, the example that I'm doing here, you'll notice that I drew pictures of Euclidean vectors. Right? This was intended to represent vectors in R2, but then you will further notice that I wasn't writing dot products, I was writing inner products. That's just for sort of ease of generalization. If you want to do this same kind of thing in a general inner product space, same formulas, exact same formulas. It's just that now the vectors are abstract vectors in an abstract inner product space. I can't visualize them exactly, but they behave as if they're vectors in Rn. So I can draw the picture in Rn, for my sort of conceptual convenience, all the formulas are correspondingly analogous. Okay. All right. Okay. So, by the way, etc. If you find yourself with a 4-dimensional basis that you want to orthonormalize, fix the first 2 vectors, just like we did on the previous page. Fix the third vector, just like we did here. And then now, what am I going to do to fix that 4th vector? Well, now that 4th vector, I need to fix it with respect to 3 previously fixed vectors. There will then be 3 terms to subtract and then normalize. Okay. All right. I'm going to let y'all read the rest of these details of this example. I'm going to talk about a couple of aspects of it, but notice all I'm doing, I've normalized the first vector. I'm just plugging into the formula, right? So there's a normalization of the first vector divided by magnitude happens to be 7 there. That was convenient. Okay, second vector. To fix the direction of this second vector, you take that second vector and you subtract off the part you don't like. The part you don't like is in the direction of V1. Here's V1. We already fixed V1. There it is. It's in the direction of V1, and how much in the direction of V1? Well, look at the projection of W2 in the V1 direction. That's this dot product. Arithmetic ensues. Then normalizing, and then to fix the third vector, just like on the previous page, you're going to subtract 2 portions. There's the portion in the direction of the first fixed vector. There's the portion in the direction of the second fixed vector. That gives you the direction fixed vector. Yikes. The arithmetic gets a little annoying. Apologies. That's how it works. And then don't forget to normalize again. Okay. All right. So the one thing I do want to show you, there's a trick on normalizing vectors. This is a really clever idea. This will save you arithmetic. Let's look at this vector. By the way, so the punchline of my story here is going to be that I did this in a very inconvenient way here. So let me say not so much wrong as like unnecessarily difficult. There's a much faster way to find the normalized vector. And that is to realize that this vector here, got some vector, and if I want to find the unit vector that points in that same direction, sure, divide by the magnitude. Yeah, right, fine. Okay, cool. But how about instead, notice that if I multiply my original vector by any scalar, any positive scalar, and then normalize, I'll get the same thing, right? There's nothing magic about that original vector. Scale it however you want by a positive factor. The unit vector that points in the direction of the purple vector is exactly the same as the unit vector that points in the direction of the dark green vector. So here's what I should have done then. I should have said, I don't like that vector. It's got fractions in it. The numerators have common factors. Those numbers are unnecessarily inconvenient. So how about I multiply this by positive scalars to the point of, how about we'll look at instead 0. Let's just get rid of the 5s in the denominator. We'll throw that away. Oh, now there's a common factor of 4. Let's get rid of that. That's all free. How about I normalize that vector instead? Right? So you can, I suppose, compute the magnitude of this vector full of fractions and then divide. Or you can compute the magnitude of this vector full of nice, easy integers. And you get the same answer with much less effort. Everybody see the trick? I'm a big fan of this little shortcut. And so you see what the alternative was, I skipped a bunch of the arithmetic in between here, but this is still quite a bit more work. Okay. All right. Okay, so section 9.3. This is a weird section. Some very strange things are going to happen in this section. I'm going to start off with a confession. I've committed some math crimes. Nobody caught me. Let me tell you what the math crime was. Long ago, at the very beginning of when we were talking about vector spaces, I commented that we were looking at vector spaces over the reals, which meant that my scalars were required to be real numbers. Right? You go back to chapter 2 in the notes, and there's a comment there that, well, when you're doing scalar multiplication, the scalars have to be real. Okay. And then what did we do in chapter 4? We had solutions to a differential equation, and we were playing fancy games with taking linear combinations to get rid of these complex valued solutions, to reproduce, to recover real valued solutions, because, hey, we live in the real world. We want real solutions, right? A mass on a spring will never run around in a circle in the complex plane. It just doesn't, right? That's not how it works. So how do you turn a collection of complex valued solutions into corresponding real solutions? Well, with linear combinations, and if you look back into the details, the coefficients were complex. And we're not allowed to do that. Everybody see that? So, like I say, a little math crime. Now, if you're worried about whether that means that all the solutions that we found in chapter 4, they're all wrong. No, not at all. So the reason I did that little math crime is because I knew that there's a way to fix that, and it's simply a matter of sort of worrying about formalities that at the time would have been a distraction, and we had enough going on as it was, and so I decided to commit this little crime and then come back and apologize for it later, and here I am, ready to fix it. So all of that, all of the little crimes that we committed in chapter 4 can all be fixed. And we don't need to worry about that part. Okay. So why am I, if I swept it under the rug in chapter 4, why am I bringing it up now? You might wonder. And the reason is that now we're getting to the point where if we were to continue committing this little crime, if we were to continue to sort of just treat complex numbers, they're effectively the same as real numbers, who cares, what's the difference? We would get into real trouble, and we would find ourselves committing mistakes that can't be fixed and that are wrong, and we would get dramatically false answers to questions. So we're going to have to start worrying about our scalars. Annoyingly. So, by the way, if this were a more advanced math course than it is, we would define something called a vector space over C. Over C is just a way of saying that you allow scalar multiplication by complex numbers. So said differently, vector space over C means you are allowed to have complex scalars, complex scalar multiplication. And I'm not going to write down definitions and develop theory on that because we kind of don't need to, and we also kind of don't have time. But it's a general idea. All we're going to talk about is specifically the complex plane and complex vectors. And how do we understand them? What does it matter? How does it change things if we view them as vector spaces where we allow complex scalars and it doesn't matter, and does anything go terribly, terribly wrong? And the answer is yes. Something very, very terribly weird happens. So let's talk about this over C. We allow complex scalars. And I claim that the complex plane is one-dimensional. If you allow complex scalars, complex plane is one-dimensional. Now, how could that be? This is, at a glance, garbage, right? It's a plane. It says so somewhere. I guess I didn't write it down. But C is the complex plane, and the plane is two-dimensional. Clearly, right? How can it be one-dimensional? Well, it's a simple matter of writing down the algebra. I claim that every vector in the complex plane, whatever vector you have in the complex plane, I can view that vector as being a multiple of 1. Every vector in the complex plane is a multiple of 1. Now, very importantly, when I say multiple, we're talking about multiplication by a scalar. And scalars are now allowed to be complex numbers. So what complex scalar do I multiply by 1 to get z? How about z? Right? So every vector in this vector space is a scalar multiple. Keep in mind, we're allowed to have complex scalars. A scalar multiple of this single basis vector 1. How many elements are there in this basis? Well, there's only one vector in this basis, and so the complex plane is one-dimensional. If you allow complex scalars. So that's the the weird thing. So now imagine this is something that is terribly, terribly different, right? This is not like the little crime we committed in Chapter 4. In Chapter 4, that's just linear combination games, and ultimately, like I say, that can all be fixed, and nothing would. The ideas there are ultimately the same as what we would have otherwise done. Here, changing to allow this seemingly harmless concept of having complex scalars has changed our notion of dimension in a weird and seemingly unacceptable way. Yeah? Everybody on board? Okay. Here's an analogous example, and I'm going to let you guys fill in the blanks on this. I'm sorry, I got ahead of myself. Exercise for y'all to persuade yourselves of. If you look at it as a vector space over R, namely if you only allow real scalars, then 1 by itself is no longer a basis, but 1 and I together as a pair becomes a basis if you require only real scalars. 2 vectors in this list, therefore two-dimensional, as it kind of should be. Okay, all right, so another example, and I'm going to let y'all do the details here, but Cn, it's just like Rn, but you allow complex coordinates. Right? But just an ordered n-tuple of numbers, now the numbers are allowed to be complex. This can be thought of as a vector space over C. So in other words, you can allow complex scalars, do complex linear combinations, and with that notion of scalar, you can compute the dimension of Cn, and the dimension is n. It's a great exercise. Give it a try. Find a basis for Cn over C. Hint, standard basis. Right? But persuade yourself that standard basis is a basis for Cn if you allow complex scalars. But if you want to talk about Cn with real scalars, it is 2n dimensional, not n dimensional. Okay. All right. So the big punchline, the main reason I wanted to talk about these 2 examples is to persuade you that even though whether we allow complex scalars or whether we stick to real scalars, this choice about scalars that was, again, I claim harmless, irrelevant, nothing to worry about in Chapter 4, is something to be very worried about in other contexts. Right? So the notion of dimension changes. And here's some other bad news. The notion of a dot product changes. This is super weird. Here's our good old dot product. Right? You have 2 vectors v and w. You multiply the coordinates, add up the products. I mean, plain old math 212 dot product. Most basic type of inner product that we have. If you apply that formula to this vector, you get 0. It's simple arithmetic, right? Multiply it out, and you see you get 0. And this is very disturbing. This is very, very, very bad, right? Look at the list of, the defining characteristics of the dot product that we wrote down a few days ago, right? One of the 4 defining characteristics of the dot product, the last one, is that only the 0 vector is supposed to do this, right? Only the 0 vector is supposed to be able to dot with itself to give you 0 as a result. And now this is very clearly a non-zero vector that's giving me a self-dot product of 0. Okay, so this is very, very bad, right? This means that even the dot product doesn't behave like the dot product is supposed to behave when you're in CN. Okay, so very bad. How do we fix it? The answer is we throw away the old idea of the dot product. We define a brand new kind of dot product called the Hermitian Dot Product that, just as it turns out, makes loads of sense in CN. The formula for this Hermitian Dot Product, we denote it like this. Note the little subscript of H. Here's the formula. It looks a lot like the old dot product. Just don't forget to conjugate the coordinates of the vector on the right before you multiply. Said differently, don't forget to conjugate before you do the transposed matrix product. This new form of a brand new dot product has properties that are pretty much what we want dot products to have. And I'll talk about the details next time. I'm out of time now. But we're going to have this new notion of dot product to allow us to do business in CN. Okay, y'all have a great Thanksgiving. See you later.